Hi guys, I'm Łukasz. I'm lead AI engineer that specializes in inference and backend engines. And today we will talk about why everybody is so obsessed with training and how many GPUs you need and so on, but instead they should be interested into the inference. So if we look in this chart, we can see that in the life cycle of AI model, training only accounts around 10-20% of the total cost, and inference accounts for 80-90. So what does it tell to us? Well, if you screw it up, the inference, you are bleeding basically money for the business. The issue is that training, it's basically costs. So it's like a spending, yeah? They need to spend money to train the model before they get any value out of it. So nobody likes training in business. But inference, this is where money gets generated, because by optimizing inference, you can serve more users cheaper and all the savings go to your pocket, let's say like this. Now, when you deploy an LLM, you are fighting two things. One is a latency, so how long the user will wait for the request. And then another one is how expensive it is. And this typically comes with VRAM. Why VRAM? Because the graphic cards can't allow you, in most cases, to load full model in one graphic card, so you need multiple ones. So then you need to figure out communication between them and everything like this to basically judge how expensive is it to serve, if you need more GPUs, if you need more VRAM, and so on. And there are multiple ways and engines to fight it, but today we'll look into two most popular ones, in my opinion, which are vLLM and SGLang. So let's dive in. Now, to understand why this is a big deal, we have to look at how an LLM generates text. We use the most popular transformer architecture, and it happens in two distinct phases. First phase is the prefill phase, and second one is the decode phase. Now, in the prefill phase, it occurs when the model first receives a prompt. The model processes the entire input sequence simultaneously, as you saw here. So we get all of this immediately. And it is compute bound, meaning it requires high GPU arithmetic to output because we use parallel matrix multiplication. And it also generates the first output token, which in this case is the Google, that we will use in the decode phase. So in the decode phase, we generate the remaining response autoregressively, which means that the model generates one token at a time. So we get this token and all this context, and we generate slides. We then we take everything from here and generate like, and then so on. So the model generates one token at a time, and then it uses previously generated token. And now KV Cage basically got created in the prefill phase because it got built while we store the intermediate attention states of all input tokens. And why we do it, and also this, to avoid recomputing them later, because we'll need to use them continuously for the decode phase. So now we can see that we have these KV vectors and they are getting caged. So basically, when we created Google, all of this was in cage, then we created output and also cage it, so we can use it for generation of the next one, and so on. So because this process require this cage, we say that the decode phase is compute bound. Why? Because it's limited by the memory of the KV cage to basically get it back. So if we didn't have this cage, the model would have to reread the entire conversation from scratch every single time new word gets generated, and that would be really slow. Now this is a nice visualization that I found on Hugging Face, so I would like to play it. So this is the first case. So when we generate without KV cage, so we generate token one by one, and we need to repeat the same calculations each time. Okay. Now let's back into visualization. So here we will see the process. So when a model generates text, it looks at all the previous token to predict the new one. So normally it would repeat the same calculations, which is super slow. So as we can see, to get another token, we'll need to compute all of this one by one. Now let's see what happens when we have KV cage. So this solves this compute overlap by remembering these calculations from previous steps, and we achieve it by storing these intermediate states of attention layers during interference. So here you see the blue ones are which ones we remember. So we only compute these yellow ones, and now we'll only compute 4 instead of all of these blocks. That's like pretty simple, but I think intuitive explanation of how it works. We can go into details, guys. If you want, just hit the comments or let me know. So now regarding KV cage, I will use the vLLM paper, Efficient Memory Management for Large Language Model Serving with Page Attention, and to explain a few examples. So key value cage, which is KV cage, this is a memory for each request, and it grows and shrinks dynamically. This is quite important, yeah, because we can get requests that have 5,000 tokens. Let's to simplify it, say 5,000 words, 2,000 words, 100 words in total. So how we will know what to do with them? If we don't, in old system, we just allocate 5,000, so the maximum possible. And then if we get 100 words, then the all memory is completely wasted for the rest. So for 4,900, for example. So we manage it inefficiently. It's quite costly, yeah? And here we can see that on some models, the KV cache takes like 30% and so on. Now, to show the memory wastes, we can look here. So now if you look, the orange one is the reservation, then internal memory fragmentation, and then external fragmentation. So basically red and gray is the waste, this is tokens, and this is reservation. So probably model loading weights and so on. So as we see in the beginning, there was a lot of waste, like 60% memory that we used basically don't do anything. So what vLLM tried to solve is to, if we allocate KV cache, that it will be dynamically used, managed, and so on. One thing that I mentioned before, so the prefill stage, we can compute it using parallelism. Why? Because this is typical matrix. Now, you could say that we could do batching. Batching, it's like feeding everything in, let's say, 50 requests together and then solving it. But the issue is in the serving models, in the inference, you get requests at different point of time, yeah? Like you can get sudden burst of 100, 200 requests, and then you can get them 10, 20 with some space of time, yeah? So if we do the batching in standard way, we'll have delay because the first request will wait for the last request to arrive when we get the 50, let's say, and then we compute it. So the first user will wait the most. I mean, the first requester. So how to fight it is that we have iterations. So basically in vLLM, there is scheduler. And what happens is you can allocate how many requests you want. So you do quick, small iterations. And if the request will not come at specific time, then, for example, only the one request will be computed so it don't wait. So basically, it will look at the load and adjust it. So we don't have any waste in this case. Now, this is a nice example. So what I said before, in old systems, so you allocate a lot of memory. So in this case, for example, let's say we allocate 2048 tokens with these ones. So we can see here the state request for prompt and then generated tokens. So father is brought forth. And then there is also like kind of, this is basically tokens that signals that it's the end of output. So you know you finished. But in old system, you then wasted memory on reserving space that you basically will not need because you finish it already here after 7-8 tokens. So you waste 2038. And then in another example here, if I remember, it was 512, yeah. So we get 512 size of requests, but our request basically finished already here, so we waste 507 slots. So this is internal fragmentation, this is reserve space to continue output and so on, and then external fragmentation, so the difference between the requests. Okay, guys, so now this will be time for test. So here we'll use vLLM and SGLang. So just to quickly remind you, vLLM use the page attention of the paper that we look for, and technically by the architecture, it should be pretty good for variable of requests, and that should be its advantage, but take it with a grain of salt because it all really depends on what's the current update, state, and so on. For example, when I try to prepare everything to make these tests, vLLM worked perfectly and I couldn't run SGLang at all. It crashed my virtual instance, but I waited 2 weeks and suddenly SGLang started working and vLLM stopped working. So then I checked that actually there is new CUDA version now, 13, that was in the newest version, and I used 12.8, which is now old one. So yeah, live. So use the engine that works. And SGLang is based on the page attention and vLLM, but it uses radix attention. You can imagine that it's like 3 attention mechanism. I will not go into details. If you want, we can dive deep into it next time. But basically, its benefit is multi-turn conversations or like code assistant and so on, because the cache should manage better the same conversation length and so on. So when you start feeding things into the memory and context and so on. So the test we'll use is here. So we use bench serving tool from SGLang. As we can see, we can test different endpoints, engines, and so on. You can define a number of prompts and endpoints, dataset, and so on. We'll use RGPT with like real prompts, examples, and so on. And you can define how many requests you want and so on. So basically, if you know your load, input, output, you can play with it. What we'll do is that we'll play with the worst case scenario. for it. So we'll do burst of all 1,000 things and see how the engine manage it. So here is quick look of the Docker, but there is nothing special. I just optimized GPU memory utilization. I tried to play with maximum number of sequence, but I thought that it would be better if we play it in default, because that's what most people will probably do, and see what we get. And I only sent the context to 10,000 max model length. And now the hardware that I use, as I said, virtual machine. So we have AMD EPYC 9374F, and I defined that I will use, this should be visible here, yeah, 14 vCPUs, 32 gigabytes of VRAM. And if we now go to NVIDIA SMI, yes, so as I said, I use VMware. So in this case, I have actually vGPU, which is L40S 48C profile. C is for compute. We see that vLLM is already loaded here. And the maximum CUDA version is 12.9, so that's what I defined, and I use driver version 570. So this I will actually need to update, but yeah, it will take some time because it's needs to be updated of server and so on. So yeah, so that's what we'll have here. And also maybe some interesting quick look. For example, if you want to play with parameters for vLLM, there is ng arguments. It will be linked in a README file on GitHub, so you can check it later. For both of them, there is something like this, but for now we are I'm showing the vLLM one. And also there is Slack, so you can ask questions here, and there is actually a nice bot that answer you quickly before people answer you, so that you can use it here. And it's use the documentation of vLLM, so it works pretty well. You can also feed from GitHub ingress the full vLLM repo to the notebook LM and ask questions there. We'll go through it maybe at the end because it's quite nice tip. So yeah, now let's look at our Docker. So as we can see, there's few caveats here, because I think it don't recognize my GPU because I have this S version. This is very nice print of computing, but yeah. Oh yeah, you can see that there is CUDA arch list issue, but I think it's pretty invisible. So let's get this maybe on one. Yeah, terminal. Now it's much better. So we define 10,000 tokens, and that gives us 9.31 concurrent requests. This is automatically defined. Yeah, and as you can see, I have this issue that I'm using suboptimal maybe solution, I think, because it looks for L40S, but we use L40S C version, which is vGPU, and vGPU are typically not very well and easy to run. So this could give us some issues, but we'll go through benchmark. If there are any issues, I will rerun it later and provide new scores or something. Yeah, perfect. So what I do here is, as I said, we use ShareGPT, 1000 prompts, full burst, 10 warm-ups. This is important because most of these engines, they actually compute CUDA graphs and everything to be ready for inference. So your first request takes actually quite time. It could be even 2 minutes. So we need to warm-up model to get actually authentic results. So I can already start it, and then I use Quencoder FP8 version. So technically you need to check it if your GPU support it. L40S should support it, so it's fine. And now if we jump here, we should soon see exactly. We are getting some pings requests because we are doing warm-up, starting benchmark run. You can already see, bang. So we have 1,500 average through output. We get already some generation, 55 tokens per second. We get 52 requests. And already we can see that 946 are waiting. And gradually we'll also see the increase in KVK. So it's 17%, now it's 70. This basically show us what's happening from time to time. That was maybe not recently, but not that far into the future in the past added to vLLM. And we can see the memory utilization. As you can see, there are jumps. It increased basically with burst of compute and so on. The actually utilization is at around 25%, which is quite good. So we are going now through all these requests. And as we can see, the queue is decreasing. The KVK is increasing, nearly full already. And if we go to the bench, we can see we already are over 190 prompts, inputs, and so on. So now with the power of video editing, okay guys, we are back with our results for vLLM. We can see that we succeed in all requests. It lasts 585. The request output was 171. Peak concurrency 1000 because we sent all of it. and total token through output and concurrency, and also other parameters. But we'll compare it on a graph, I think, at the end anyway. So to quickly jump back, let's also show. So this will be the image that we run. It's also based on the documentation of SGLang, and I set it to also 10,000 and the same model and everything default. This is just one GPU. And now we can see I prepared the test, and let's see if the model wrote it. Not yet. So here we can also find out that there will be the same issue as on vLLM. So because I use vGPU, it don't recognize that it's L40S, so you don't know which shape to assign. But we'll learn it anyway. Okay, so it loaded, and the interesting part is if we look at concurrency, we see there is concurrent calls 32, so we'll see how many requests it could manage. And now maybe to quickly jump in, let's start the benchmark. You can look what's going to happen. And also here is everything with CPU and so on. Okay, we see requests. And we see spike in GPU utilization. So running requests 4, 6, 77, token usage, cage tokens, prefill batch. Oh yeah, now it's better. And we can look at the test. Okay, so we started 6%. We'll see how quick it is at the end and compare the parameters, because here, okay, yeah. So just quick note, SGLang repo is on GitHub, 22k GitHub stars. vLLM have 78. They also have help desk, and actually I don't see here AI to help you, so it's mainly people helping people, so a bit different. I think the AI in vLLM actually work quite well, because you can get instant answer before anybody check your message. Of course, documentation with different GPUs and everything you need to know that you can read. Well, they have Ask AI also. But I don't see SGLang. No, they have SGLang bot. Okay. So it should probably work the same. Let's see how to run Docker with when. Let's maybe see to suggest us the same Docker. Control C. Okay, we are back. So as we can see, there is also bot, and provide us Docker. I think it seems okay. Here they suggested that we don't let model in separate instruction using Hugging Face CLI. Maybe it makes sense. Maybe it's faster. I never compare it, so I'm not sure. And also it's added that we need to check if we support FP8, so it's quite good. So now we'll be back when we finish the test, and we are over 200 requests more. Okay guys, we are back. We get SGLang results, and also nice to mention, we get created files here of these runs, so we can always compare it, put it into Excel and so on, which I will do soon. And for now, I put it in. So let's look. 1,000, okay. Benchmark duration 585, 789. So that's significant difference. Request to output is also much lower on SGLang. Input to output, yeah, of course, too. Peak request, yeah. Concurrency, latency. Okay, so results are quite surprising for me. I thought it would be more close. And also, remember, we use not even newest version of vLLM, because I couldn't run it with CUDA 13. So the results, are quite interesting. I will also check if I can easily define that use L40S GPU, so the profiles will be right. And I'll come back with these new results then. And I'll also put everything in Excel, so we can look into it with a bit more graphical view. So stay tuned. So I'm back with the results. I also checked the errors that we have before with the documentation of vLLM and so on. So actually, not only vLLM, but SGLang. Actually, there are scripts, so I should run them to optimize my kernels for the GPU that I use. And because I use C, I don't recognize that it's L40S, or maybe there is some differences. I'm not really sure. It's really hard to find anything. But I I run these scripts and they failed, or one succeeded, but I need another one to even make it properly. So we'll follow these results. So first thing we can see is that the duration for vLLM is much lower than SGLang. This is also visible here. And because of it, we can see that the request output was much higher for the vLLM. The concurrency was a bit lower, which means that the scheduler probably allowed less concurrency and SGLang allowed more, which resulted in lower request row output that we can see here because it's a low number, but yeah. And we have the input, output, the total output. So as we can see, there is big difference here. And the total tokens more or less are the same or very close. There is like small difference here, but it's nothing big. So now if we jump to other parameters, we have E to E latency. So that's total request time. This is basically waiting and full generation. So as we can see, this is in milliseconds. So 220 milliseconds is the number that it takes vLLM to finish the total requests with waiting and full generation. And for SGLang is 355. Yes, this is also visible here. So as we can see, vLLM was winner also in all of these cases. So basically what it means is that the long initial wait of SGLang kit perform worse in E2E latency. And then if we look in TFT, which is here, so TFT is the time to first token. So it's time from request arrival to the first generated token. So it's dominated by queuing and scheduling. So vLLM is again winner. As we can see here, it get 138 seconds and then 295. So this means that under the load, the request waited longer in SGLang before it even started decoding, and it's reflected in this score. Now in TPOT, this is time per output token. So it's average time to generate each token. It's pure decode efficiency. And this is quite nice because we can see that SGLang win here. So that means that SGLang, when it gets to the decode, provided much efficiently, faster, so it takes less time to generate token. It's 145 times faster than vLLM, which means that we get 1.45 tokens compared to 1 token from vLLM. And then we have the last one, which is here. Okay, so now we have last one, which is inter-token latency, ETL. So it's gap between consecutive tokens. So it's like kind of smoothness. So SGLang streams tokens more smoothly and frequently, which is again related to Decode, and it's also beneficial for long output and streaming clients. So from this, we can say that vLLM is better at batching with starting early decode. So basically putting the things to decode faster, and we can have dynamic batching, and it's basically optimized for many concurrent requests that are different, which makes sense for the page attention. And for the SGLang, we can see that it's decode centric. So basically we will have better generation of the decode. So that if we have really long decode phase, like really long output, like summary or really long conversation or something to add there, and then send request, then it should dominate in this use case. So yeah, that's it. So if you like it, please like and subscribe so I know that you guys like the video, what was good, what was bad, and see you guys in the next one. Bye.